So first of all, you forget what it said about my topics. Okay. So I've been teaching similar things at the summer school for many years, and it's always interesting to interact and make small tweaks, but this time I decided to do something completely different. Okay. So that means you guys are going to have to help me out, because it's not only the first time I'm teaching it here, it's the first time I'm teaching it, period. And also, by the end of the last lecture, you should be at the edge of my current state of knowledge, okay? So that's a pretty tall order, okay? But, I don't actually know that much more, okay? So my new title for my lectures is going to be Adjoint Functional Programming Okay, so adjoint is scary because it sounds like category theory. Okay, so don't worry, there's no category theory in any of my lectures. Functional is fine, right? We all love functional. Programming, we all do anyway. But actually, in today's lecture, there won't be any functions. But by the end, we'll have some functions, okay? So lecture 1, okay, is going to be linear functional programming. So there has been a lot of interest recently in looking at this concept of linearity. You might have heard of it, okay? Its origins are in something called linear logic, which stems back to 1987, according to some people even before. And its potential for programming languages was realized early on, but it took a long time to actually realize that in real programming languages. And in programming language research, it seems to be often the case that the translation from a theoretical insight to a sort of working programming language to people in industry using it can be a long lag, okay? On the other hand, there are now languages out there that people use, okay? For example, Rust. Who here has programmed something in Rust? Okay. So you're overqualified, so you can actually go now. Okay. The rest stay here from my first lecture. Okay. So this idea of linear programming, or more generally, like I call it, substructural programming, is now actually coming to real programming practice, including industry. Okay. So I've always been interested in that, but just over the last maybe 2 years, I've come to seriously pursue that, and not in the context of Rust, but in the context of functional programming, because functional programming is more closely related to the logic compared to imperative languages like Rust. But there's still a lot to be learned. And I found that a very fascinating journey, and so I've decided to try to take you along on that journey, okay? So what I'm going to try to do today is give you an introduction to linear functional programming, and you'll find that it sucks, okay? All right, but that's okay because that's the impetus for the next step, right? But there's also many cool things. And so the overall goal of the lectures is to start with a very simple language and build it up over the course of 5 lectures. And at the end, to have an interesting language and also understanding of a compiler, okay, from this language down. In my case, it turns out to be that the eventual target is C, but Ankush Das and I, trying to correct that eventually, we'll see if we can compile it to Rust as well. Should be a decent match, but I don't know for sure until we have done it. So what's some of the features of the language, okay? So this is looking forward, okay? So the language is called Snacks, by the way. And I'm not trying to explain the name. By the end, you know what it means. It doesn't have anything to do with junk food, okay? It has to do with proof theory. Yeah, by the end you'll know what that means. And so, so one of the features we have is substructural programming, so linear plus nonlinear programming. Okay. We have inference. And inference means that you can write your program pretty much, maybe I'm overstating the case, being unaware of, for example, if your program should satisfy certain strong properties like linearity, which we'll talk about in today's lecture, or some other properties, and the system will do inference for you. It has overloading in that sense, so you can write the same function and have it work differently depending on whether it's linear or whether it's nonlinear, but it's only one function that you have to write. So overloading. And then we have lower level languages besides the source language in which we actually write the code. And in these lower level languages, they have something interesting in it, which is that they're still motivated by proof theory. So the source language that we're writing is directly connected to certain kinds of logics, as are the intermediate languages. Okay, so we're not giving up sort of on the logical foundation of our programming language until we get to C. All the way up till then, everything will be either natural reduction or sequent calculus or things of that nature. Okay, so the whole thing that we'll build is, I call it a proof theoretic compiler. Okay. Proof theoretic compiler. And I'll try to explain at various points what are the connections between the language that we design and the proof theory that underlies its design. For me, it's mostly an aesthetic thing, but it's also a notion of finding that, yeah, we've done the right thing. If it has a logical explanation versus, oh, we can execute it, those are two different things. If you can only execute it, you feel good about it. If it also has a logical foundation and you know it's connected to logic, then you feel even better about it. Okay? I mean, that's somehow what we're trying to do. Okay, some of these things may not mean anything to you, but a lot of hands went up when I asked about Rust, so some of these things mean something to you already at this point. Okay. Okay, so let's start with our language. There's probably some other features of the language that I'm missing right now, but we'll get to them, okay? By and by as we go through our lectures, okay? Okay, so to understand a programming language, we usually start with types because there's usually few types, and types are the organizing principles for a programming language, okay? So types. And we want somehow as few types as possible because we get smaller languages, okay? As long as you can still say what we want to say. Okay. So when I recently had a birthday celebration, and Chris Martins, who is in the back there, who's my TA and who's attending, they actually talked about my tendency towards language minimalism, which is that if there's something you don't need, don't put it in the language, okay? So there's, you know, that's painful sometimes, okay? So I want you to feel that pain, okay? It's very important for me that you feel that pain, okay? Because then you know, oh, that's why we do this thing, that's why we do that thing. And then you kind of figure out how things fit together, okay? By the way, I should say that this compiler we're building, actually, even though it's based on proof theory, like almost all the way down, actually gets very good performance for a wide range of programs. Comparable and sometimes better is something like the Milton compiler for standard ML or Camel. So there is something to be said for it, okay? Besides the fact that it has a good proof theory. Okay, so today we'll start with types. Okay, what's the simplest type that you can think of? Well, there's two simplest types, the empty type and the type that has one element. Okay, I hate the empty type, so we don't have that, okay? So we'll have a type with one element, and we call it 1. Okay. And what's the element? Well, the element is that, and we say, well, this thing has type 1. And that's our inference rule. Then we have to think, what are the values of the type? Well, in this case, this is the only value. And so I've now explained this type to you and say, well, the only member of this type is like this empty bracket here. That's the only value of this type. Okay, make sense? All should be pretty straightforward. Okay. So it's become more complicated, right? The next thing I want to do is a type with 2 elements. Okay. So how do I get a type with 2 elements? Well, I could do something like 1 plus 1, right? Which is 2. Okay. So that should be a type with 2 elements. Okay. But it's not so interesting that it has 2 elements. Because, for example, what would be a type with 3 elements? Right? Which is 3. Okay. So the interesting part here is not the 2, but the interesting part is the plus. Okay. So this thing is the thing that matters. Okay. The plus. So it takes 2 types and constructs a new one from them. By the way, because this is the first time I'm lecturing about this stuff, well, not exactly this, but as we're going along, I'm going to need your help, right? I'm going to ask you a question. I need to know what you can follow and what you can't and where I'm screwing up and stuff like that. Okay. So here we are. So what's the plus construct we actually do? Okay. So in general, we have a type A plus B. Okay. We want a value of this type to be either value of type A or value of type B. But we also want to know which of these 2 things we're in. Because a value of type 1 plus 1 is either the thing over here or the thing over here, and I need to be able to distinguish them. Otherwise, I would just get 1 again. It's just a single element. Okay. So the way I'm going to say that is that injection on the left of the value v, or let's just write expressions. Values are subtypes of a subset of expressions. I'm just going to write expressions. Is upon A plus B if E is of type A. By the way, can you read this in the back? We're doing OK? All right, good. All right. So then here, and if E is of type B, then the injection on the right of E is of type B. OK. And A plus B. There was an audible gasp in the audience. Okay. So that's exactly the kind of thing that I need. Okay. All right. Did I get it right this time? All right, good, thanks. Now, what are the values of this type? Well, I want the values to be an in left of a value here or an in right of a value here. So in left of V is the value, if V is a value, and in right of V is a value, if V is a value. And now I can prove that, for example, of type 1 plus 1, there should be exactly 2 values, namely in left of unit, and maybe we can call that true, or it could be in false. That could be in right of unit, where these parts here are completely arbitrary. Okay. Now, working with the binary sums is kind of a pain, okay, when you write programs. Because if you've done any kind of functional programming, you know that we can data type constructor with many different cases. So we don't just put 2 things together, we put many things together. So what we're going to do in order to allow this is we're going to have a sum plus, where we have some labels. I'm going to underline these now. They might all have different types. And they're drawn from some label set L. And I'm going to say L is not the empty set, and it's finite. Okay? So for example, the old A plus B which I just showed you 2 minutes ago, well, it's already obsolete, okay, is just now being defined as the sum of in left colon A or in right colon B. Okay. Does that make sense so far? Everybody on board? Okay. Okay. So then I probably would define the type 2 this way. I would say the type of Booleans is a sum between true, comma 1, or false, comma 1. But you have to remember that these things aren't exactly the same thing as this thing over here. These are tags. So now true applied to unit is of type bool. And the tag false applied to unit is also of type bool. And these are the only values that have of type bool. Okay. So being able to sum up types that I already have creates fresh types that have interesting structure. Okay. But so far, the structure is not very rich because I can only have finite types. Yeah?
Why did you put these side conditions in the label set? Will it matter later, or is it just a personal preference?
No, it will matter later. So in the implementation, for the most part, the label set can be empty. But it complicates the implementation by an order of magnitude, unfortunately. And I'll explain at some point why, not in today's lecture. And the finiteness is important because you need to somehow represent them in this way, where each label is a given word. Okay. When you compile it to C, finiteness is also nice. Okay. Okay, other questions? Okay, so now, yep.
Can that be recursive?
Good question, because I was just going to give you an example of a recursive type. Okay. By the way, Tesla is another honorary of mine because he took my course on substructural logics last fall. Okay. So some of it, most of what I'm going to talk about is repeat, but the implementation only started to exist yesterday. Okay. So he didn't get exposure to that. So, okay. So if I wanted to represent the natural numbers, okay, so it's a sum of two things. It could be either 0 and then there is nothing, so of type 1, and this is a tag. So that the number 0 would be represented as, so let me write it like this. The representation of 0 is the tag 0 of unit. Okay, we good? Okay, or it could be a successor, but then the thing that it tags is another natural number. Okay, so now we have one thing defined in terms of itself, but this kind of recursion is necessary to define the natural numbers because there can be infinitely many of them, but with a sum you can only combine a finite number of things. Okay, so then the representation of 1 would be successor of 0. And the representation of 2 would be the successor of 0. Okay. This is something that's in the literature, something called equirecursive types. In the sense that we always think of NAT as really being equal to this type over here. Not in some sense isomorphic or anything like that, which are isorecursive types, but equirecursive types. That will play a role later in the language design. At the moment, it just makes it easy to write programs because we don't have to worry about these isomorphisms floating around in our terms. Okay. Okay, you can see how complete that, right? Pretty easy. Okay, so we need typing rules for this construct, right? For the plus. So let's see if we can pull this down. So it has to be somehow like these things over there. So something has type plus of L colon AL, where L is from some index set. Okay, what does it have to look like? It has to look like a label. Okay. Okay. Apply to some tagging some expression E, where the expression E has which type? AK, right? And it better be the case also that KB in the index has, otherwise it doesn't make sense, right? Make sense? So we pick out the part of the sum that we want E to be in, and then we have to look up this type here. That's the type of the thing underneath, right? Okay. So if we look at something like this, we want to type this expression here and prove or show that this is type nat, which a type checker will do. It's C's successor. Okay. Now this over here is equal to this type over here that really is a sum. That's an easy thing to say because it's an equirecursive type. So it's one of these pluses thing here. We go through and we see, okay, there's a successor. So that means the thing underneath here, this thing, has to have type nat. Okay, 0 has type nat. We go back, we expand nat, we say, okay, it's 0. So the thing underneath has to have type 1, and that's the unit type, so we get that over here. So it all works out. And the values are also easy to define because K, tagging value V, is a value if V is a value, okay? Okay, let's do one more interesting type. So I can do one more constructor. Let's get rid of these because these are now obsolete. Anyway. Okay, so I want to do lists of natural numbers. Okay, another perfectly respectable type. So what's a list? Okay, it can either be an empty list, and then nothing. Okay, so that's the unit element. Nil tags the unit element, or it's a cons. And then what do we have here? Well, what we want is an element and another list, the tail of the list. Okay, so we want an element in that and another list. So this is also a recursive type because list is here and here. Okay, but we need this thing in order to define what a list is. We need to be able to form pairs. So we can define so far, we have a unit type, we have a general sum type, we have recursive type definitions, and now we also need pair type. Okay. So when we have two expressions, E1 pair E2, that has type A cross B, if E1 has type A and E2 has type B. Make sense? Right? If you put together a pair, well, the components have to have the right type. And when do we have a value? Well, a pair V1, V2 is a value if V1 is a value and V2 is a value. Okay. All right. So right now we only have these three things, type constructors really, plus a way of defining things like sort of at the top level, if you will, like these recursive types. Now, we also have to define values. So at this point, we should be able to represent trees. We should be able to have trees where at each node you have a whole list of elements, right? You can do all that now, right? There's no issue with defining these types. But we can't compute it all, okay? We've only defined what values are. We haven't defined how to compute with these things, right? So what I've defined so far are the rules to construct elements. So this would be a pair introduction rule. This would be the one introduction rule, and this would be the plus introduction rule. Basically, it introduces a type and also the elements of that type. Now, when we compute, we want to have one of these things in our hand. We want to do something with it. Okay, so we want to say, look at a data value, okay, and like take some operation on it. So let's try to take a very simple starting point. Okay, let's get rid of this part here. Okay, let's say I want to define negation of Booleans. Right? Okay, so I say not of x colon bool, and I want the result to return another Boolean. Okay, and then I'm going to define not. This is an O here, not an A, of x equals. Okay. So these definitions here are kind of like the definitions of nat and bool here. You think of these as being like at the meta level. Okay. So I don't have an explicit construct to form a function, but I can define one in sort of the level of discourse that I'm taking. Okay. And that's because I want to avoid, for today's lecture, introduce function types like A or B. And it'll play a very important role actually later in the class, but probably not today. Okay, so anyway, I want to find not of x. So how do I do that? Well, I have to take cases over what x is and then act accordingly. So I'm going to do match x, so this is a keyword, with, okay? So I'm going to be very particular here. So it could be true, which is a tag. And then underneath there's going to be something of type 1. So if I'm going to be very pedantic, I like to be pedantic, okay, on occasion. Okay, it's going to be, the pattern looks like this. The other possibility that it's a tag of false, applied to some u. Okay, so how many cases do I have here? Well, as many cases as this type suggests. And so there's two cases here in the sum, so there's going to be two branches here. Okay, if it's, well, all of our examples so far just have two branches, but okay. And you can see that based on our definition that u should have type 1 here and it should have type 1 here, because by this typing rule, by the typing rule over there, and this you can see that has to be the case. Okay, so now what do I do next? I have to, yeah?
This is a bit of a minor question, but I just
Yep.
want to ask, is it also legal to pattern match on the value of u? So you can match, say, true parentheses.
Yeah, in 5 minutes it'll be legal. Right now it's illegal. The question was whether it's legal or illegal to match on pattern match on u. And the answer is in 5 minutes it will be legal. Okay. Okay. Or maybe 10. Okay. Somewhere around the neighborhood of that. Okay, so in the implementation that you're going to use for your homework, and I'm going to live code later on, it's definitely going to be legal. So what happens here now? We want to construct the value false. How do we do that? False of u, which is a tag. Okay, and over here? True of u. Does that make sense? Okay, pretty easy to write. Okay, but we have this new construct match, so we need to figure out how to type that. Yeah?
Would we find also instead of you just directly do the parentheses, is that also accepted?
Actually, no. Okay. If I do this. So today, I want to do what's called linear function programming. What linear function programming means that every variable must be used exactly once. This variable u is not used. So this program here would be rejected. It says, you're not using u. Okay. the compiler is pedantic in that way. Even though you are unit type, you know what it is. Still, it's a variable here, and it's not being used over here, so that's illegal. Okay. So in linear functional programming, which is the topic of the lecture today, which you can also call it garbage-free programming, where every variable that you have in your program must be used exactly once. That means that when you start with the program, you run it, at the end there will be no garbage because variables introduced will be used. It will return a value, but nothing else. So you don't need a garbage collector for a linear functional programming language. Okay. And that's actually important, can have a significant impact. So I don't like to have ill-typed code on the board. Okay, so I'm going to replace it again with this. Okay, so now we need to type this construct. And that means, let me put it over here. So if we have match the expression E with, okay, so what do the branches look like? They look like L of X, arrow E sub L. And the whole thing has to have some type C. Okay? And how many branches are there? Well, the L should be drawn from some index set. And that index set should be determined by the type of E. Okay? So what I want here is that E has type some L colon A sub L from some index set. And then you have to type each branch, right? Every single branch. So how do I do that? So I say E sub L. Well, at compile time or at type checking time, I don't know which branch will be taken. So no matter which branch will be taken, I should get something of the same type as the output, right? When I run my program, when I run this program, I want to get an output, a result of type C. I don't know what E will be. So no matter which branch is chosen, I always want to get something of type C. Okay? And I have to do this for all L and L, okay? Because I need to check every single branch. Okay, but now there's a problem. What's the problem here? Looks like a pretty good rule, but it's a very bad rule. We don't know the type of X, right? So what's the type of X? It appears in here, right? Over there, U appears. Yeah, it has type 1. So what's the type of X? What is the type of X? A sub L, right? Because I pick out from this, and so the tag L tags some X of type A sub L, so this will be A sub L. Okay, so I'm writing a turnstile here, but it means that I have to redo everything I've done so far. Okay, and why do I need to do that? Because now we need to type check an expression which has some free variables in them. And these free variables have to have a type. And I need that because, well, when I type this kind of a program, I need to, when I run this, E will compute some kind of member of the sum. And I'm going to have to bind this variable X to whatever that member of the sum actually is. Okay. So now I have to go back and change all that. This rule is particularly tricky, so let me try some simpler ones first. Okay. Okay, so let's look at, let me get rid of the values. Okay, so you have a pair. Okay, so now I have to have some variables over here. Okay, so how do I type a pair now? Okay, so here is the first time it really becomes tricky. Okay, I want every variable to be used exactly once, right? Because I want to do garbage-free functional programming, which means a linear functional program, which means I'm going to use up all the things that are given me here to construct the resulting value. Okay, so I cannot put gamma here and gamma here, because you could write a function that looks like this: duplicate x equals pair x comma x, and that would not be a valid function because it would use the x more than once. Okay, so I can't do it like this. Okay. So what do I have to do here?
When you
Yep. I have some delta over here, and I write the disjoint union as a comma. So whatever assumptions I have, I'll divide into two. Some go over here and some go over here. And what do my assumptions look like? So gamma is either empty, I have no assumptions, or it's a gamma followed by x colon. Okay, so we just have these assumptions which tell me which variables. And we want that for each gamma, the variables are unique. So when I look up a variable, I don't want to give, it could be type bool or it could be type nat. I want a unique type. Yep.
The A there is not the same as the A on the left.
You mean this A here?
Yeah.
No, this is just generically your context gamma is either empty or it's a gamma with an additional variable of type A. Okay. Okay. And now I need to be able to look up a variable in the context, right? So how do I do that? Let me get rid of the list. So one possible type of expression is a variable. Like in our example here, I think a variable u was a possibility. So in the rule, I'll just say x. Okay, so what do I do for x? Well, I want to use the assumption about the type of x. Okay, and this is a shorthand for saying in the empty context, I just have only one thing. Why is it only one thing? If you allowed other things here, you wouldn't be using them because you only use x. So there cannot be anything else here. Everybody see that? If I left another variable here, then it would be illegal. I could define a function like this. K of x and y equals x. Okay, and that would not be a valid function because even though I'm using x, I'm not using y. So therefore, when I come to the variable x here, I would have x of some type A and y of some type B. I want to check that x has type A, but I'm not allowed to do that because it has to be the only thing in the context. Okay. Okay, so these are the rules for pairs now. We need to have a rule for pattern matching against the pair. Now, fortunately, that's pretty easy. Okay. So this, it's not nearly as difficult as the sums. Okay, so if I have a match some expression E with, what should we be matching it with? If E, by the way, when you write down these things, it's usually a good idea to write down from the things that you know. They're not always written from the top to the bottom, even though they're written as inference rules. And they're not always written from the bottom to the top. They're usually written in some kind of like information way. So yeah, you're going to say something? Yeah, so we have here E is tough type A cross B because we want the case where it's a product. And then you have to match it with a pair x comma y. Okay. So then over here we have some other expression E prime. Over there we have one for each branch. Here we have only one. The whole expression here should return something of type C. So E prime also has type C. Okay. And now we just need to fill in the context over here, hopefully in the right way. So what can we say about this context here that we check E prime in? So because we're matching the pair against x and y should be in the context, should be an assumption. What should be the type of x? What should be the type of y? B. Okay. So we're starting to approach something that looks like the correct rule. Now, we might need some assumptions, some variables that may appear in E. and we're doing it in case over. Okay. That has to show up down here. What else?
There might be assumptions on the
There might be other variables here. And where do they show up over here? Where I left the space, okay? Because I knew the answer. Okay. Okay, so from a type checking perspective, what you really want to think here is that to type check this, you have to split your variables. Some go over here to check E, that's type A cross B, and the remaining ones go over here to check E prime with some additional assumptions. That's not really how you implement it, okay? Can anybody think of a way you might actually implement this? Because when you're down here, how do you know how to split all the assumptions you have? Some go here and some go there. Yeah?
Whatever's used in E has to go into delta. There are variables, right?
Yeah. Okay, so the simplest thing is you look at E, you find out all the variables that are there, and those variables end up in delta. You look at E prime, and all the variables are there going here. Can there be any other ones? If there were, then it wouldn't be well typed. Okay, so then you say, okay, type error. But actually, this is kind of expensive because each time you have a match, you'd have to traverse the whole thing to find what its three variables are. So that's not really how we do it. Anybody have an idea how we might improve on that? Yeah?
Guessing you probably have like some set data structure or something, like in three variables, and then use that there.
Yeah, you could. Yeah, that's actually not how we do it, but there would be a clever way to do that, what I think what you're saying. Back there? Yeah?
You could extend your judgment to give back a new environment.
Yeah, so one thing we can do is we can pass all the assumptions into here. We type check that. It gives us back the ones that we either used or didn't use. If it gives us back the ones we didn't use, we pass them into here. And then this gives us back that it didn't use, and we pass them down here. Right, so we thread this set through. That would be one way to do it. That's called a subtractive approach, because type checking something will subtract the assumptions we're actually using and gives us back the ones we haven't used. There's also the additive approach, which means you pass all assumption into here, and you also pass all assumption into here, and you return the ones that you've used here, and you return the ones that you used here, and then you merge them. And if something appears on both sides, that's an error. Okay. So the implementation that you're going to use uses the additive approach, and there's good reasons to do that, which are not so obvious here. Okay. But both of them are. You can picture the algorithm, right? Even without having some kind of incomplete set of rules. Let's look at the unit, because I want to get to some actual coding. I want to complete the set of rules. So for the unit, it would be, okay, actually this one here, there has to be a context of on the left. What would that be? Empty. Why does it have to be empty? Because if there was a variable there, we wouldn't be using it because we always return the unit element. Everything has to be used exactly once. That would be illegal. Okay. All right. And finally, matching. Let's see. What else do we need? We have that. I think we have all the rules now. So we can come back to this one. Okay. So how do we do this? Part of the pattern here, okay, is pretty clear. We have some delta, and we use that over here to check to construct the E, and the E is going to be a value of the sum type. Okay, but now what do we do with the rest? Okay, so here's the answer. We have some gamma, and we pass in the same gamma to all the branches. So it looks like you're actually reusing things because it's passed into more than one branch. Does anybody have some intuition about why it's actually okay to take this one gamma here and replicate it for all the branches over here. Yeah? Yeah, because based on what E is, you'll pick out one of these branches, just one of them among all of them, right? The one whose tag matches the tag of the value of V. And so that's the one that gets executed. It's going to use up all of gamma. So each branch has to be checked with exactly the same set. Okay. So maybe, yeah, maybe we can go and write some code now. Okay. Maybe that last thing wasn't completely clear to everyone, but maybe I'll think of an example before I do the coding stuff. So let's do this on the board. We'll define plus of x colon nat and y colon nat, returning a natural number, plus of x and y equals. Okay, how do I define plus on unary numbers? Yeah? We pattern match. What do we pattern match? Well, typically, we pattern match on x, but you could, of course, equally well pattern match on y because it's a symmetric function. Match x with. Okay, so let's remember x is type nat, so how many branches do I have? 2. Okay, so the first branch will be 0. Okay, so now I'm going to make this legal. Okay. If I didn't do this, I had to say 0 of u, and then match u with the unit, and then continue. Okay. That becomes tedious, so I'm not going to do that. I'm just saying, just expand this syntactically in 0 tagging u, match u with the unit element, and then continue. Okay. Okay, and successor of x prime. Okay. Let's look at this case first. So if x is the successor of x prime, what do I do? I have to recurse. So I do plus of x prime and y, and then takes the successor of that. Or, yeah, an alternative, you could do plus of x prime and successor of y, right? Both of them make sense. Okay. This one might be preferred for some functional programmers. Why? Because it's tail recursive, right? So this would be compiling to a loop. This one would not be compiling to a loop, except, well, under certain circumstances, you might still be able to compile this to a loop. Okay. But anyway, the outcome is the same. Now, I'm going to be devious and make this program incorrect. Okay. And so the way I would do that is I'll return 0 here. Okay. Okay, so what does the first version return? If I return 0 here? X. And what does the second version return? 0. Okay, so now they're different. Now, this is an incorrect program. The question is, does it even type check? Okay, so why doesn't it type check? Yeah? Because I'm not using y. See, here, y is not being used. And that's an illustration. In the context when I'm coming down here, I have x and y of type nat. I'm using x. Good. Used up. Okay. I don't add anything here in this branch. Okay. Actually, I would be adding u, and then I do a match over u. And then here, I'm not using y, so it would be a type error would say y not used. Okay. And in fact, if I take this branch, indeed, I'm not using y. I'm not even looking at it. Okay. So not everything that are actually passed to this function would be used. Now, if I change it to the correct, which would be y. Now let's look at the first version. I start with plus xy, I match x. X is used. 0 of unit. Okay, so all of x is being looked at. I return y that's using y. Okay, so correct. In the second branch, I use up x, got access to x prime into my context. At this point, x prime is my context, has which type? Nat, because successor has argument of type nat. By the way, I've lapsed into concrete syntax here, but these are the tags, okay? So then I have successor of, okay, I use x prime, excellent. And I use y over here, good. Now in this version, I use x prime here, I use y here, okay, everything's good. So this is a linear program. It will use up its input exactly. And if I replace this by 0, it's no longer a linear program because it won't even use y. Okay. Okay. So let's see if I can figure out how to do this live coding business here. Yeah? Probably not today, probably tomorrow. Yeah. We'll see. I mean, I prefer programming, but it's important to see the rules because you want to verify that it doesn't produce any garbage, so you should see that. Yeah?
Frank, can you repeat the question on the mic?
Oh, okay. So the question was if I'm going to introduce reduction rules, and the answer is yes. I don't know if I'm going to have time today. Yeah?
So earlier you introduced two different rules for match width. Why? That's my question.
Okay, so because the construct that eliminate pairs and sums and unit are all match constructs. In one case, you match against the pair. In another case, you match against the sequence of the possibilities of the sum. And in the third case, you match against the unit element. So because they all do match, we use the same syntax, but the pattern changes. Yeah, good question. Yeah. Okay, tags and labels. Okay, so they're just a way to present concrete data values that it can observe. So maybe when I write the code, will become more clear. Yeah?
Question about, I didn't really understand what you meant when you said additive type checking and formatting.
Okay, yeah, so we'll take that offline because I will talk about the type checker another time. So, yeah. Yeah?
Have we talked at all about variable name classes?
Yes, I've said that they always have to be different.
But for the implementation, we're just going to assume that they are? Or is that like
No. In the implementation, we're going to do shadowing. So that means if you have something like, if this x here is already defined in gamma, then any reference to x in E prime is going to refer to the inner one here. Or another one could say that under the hood, this is renamed to some x bar, and you rename this x to x bar in here to make sure that it's always unique. Yeah?
Is there a reason why we didn't generalize the product type to n elements instead of just 2?
Yes, that's because we'll do that in lecture 3.
Okay.
But it turns out that the product type with n elements turns out to be lazy, and you're going to use it to represent not values of this form, but actually like, well, objects or lazy records. So they have a different meaning than the ones we introduced here. Yeah?
Sorry if I missed it, but the inference rule on the bottom left, the return type of certain type of E prime on the bottom is C and on the top is.
It's the same C. It's a capital letter C. It's the same thing. Yeah. Right, it's the same on the top of the bottom. I should have written that. So gamma k of E has type plus L colon A L L in L if, so this is a tag, E has type A sub k and k is in L. So it's a good point. It's uninteresting in this case because nothing changes. Yeah. Yeah? Right. This k has to be in the label set. And so the thing that's being tagged has type a sub k.
Is shadowing, in the case of shadowing, is even possible to do? Because if you're shadowing a variable, is it generalized by
That's a good question. Maybe not. Maybe it's not possible. Yeah, that's a good point. So in the implementation, I have more than just linear stuff. So it can definitely happen there. If it's purely linear, yeah, it may not be possible. Because when you shadow a variable, you can no longer refer to it, but we use everything. So then it would be illegal. Yeah. So you couldn't write a program that would be shadowing. So if you try to write something like k star of x, x equals x, right? This would refer to that, but this is no longer accessible. So there's nothing you can write on this right-hand side that would be okay. That's a good observation. Other questions? Yep.
In order to make the product type an instance of this match, or well, of this plus type, does a sub l need to be a list of types?
So there is one entry in this sum for every element of this list. So this list could be like true, false, or a zero successor, or nil cons.
Well, what's going through my mind is how is the x comma y the ordered pair?
Yeah.
Is that what is the label there?
There's no label in this case.
Ah, okay.
Yeah. It's just a pair, so there's no labels here. Yeah.
When you said that an array pairs will be lazy, is that necessarily the case, or are you just choosing to use it to represent something else?
Well, there's a proof theoretic argument why it should be lazy, but I think I can't make that argument at this point in this set of lectures. It's not just an arbitrary choice of mine, but there's a relationship between the sums, these n-ary sums, and these lazy products. They're actually like adjoint, I hate to use that word, to each other, and that would make them lazy. So it's not arbitrary, but it's hard to explain without, yeah. But it's a good question. If I remember when we get to it, we'll see what happens. Okay, other questions? Okay, let's do some coding. Okay, so this is lecture 1. It adjoint 0. And I think for you to see in the back, it needs to be at 180. Okay, so let's do an example we've already done. So type bool equals plus of, okay, so the underline actually is going to be like this. So whenever you have a tag, it's preceded by a tick mark. Can you see that in the back? Is that big enough, or do you need, we good? Bigger? One more? Okay, let's see. This one, doing okay now? I think I still have enough room on the screen. So when I underlined it on the board, it's actually a tick mark followed by thing. That's how you syntactically distinguish one of these tags. Okay, so then we can make a definition. So for example, not of x equals match x with, and then if it's true, now there's a secret. You can actually use this pattern matching that was legal as of 10 minutes ago. Okay, and then we want to return what? We can't return false of unit because u is gone. We have to return false of that. Yes? And if I say false, then I can return true. Okay? The only difference is that I actually have to declare the type of not. Okay? Okay, so now, so let's see if we can run this code. Why does it do that? I've never figured out to reliably get Emacs not to do this to me. Okay. 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 So now we need to do snacks of lecture 1.80J0. Okay. So what does it tell me here? Well, it didn't do any computation. It's nothing. And it produced a whole bunch of files that the compiler produces. But I don't want to see these because they're not really relevant for today's lecture. I would say out equals none. Okay, and then it would just tell me, okay, loading the file. Default mode means everything is typed linearly. There's no value. So we want the computation to happen. Okay. Okay, so we could say declare false Boolean and define false to be the negation of true. Probably not the smartest way to do it, but okay. Now it should compute something, right? So let's see if it does. Yes, and it says the value of this new thing, false, and that's just an ordinary meta-level identifier now, is false. Okay. Does that seem reasonable? Okay. Let's see what else do we want to program. We want to define the type natural number, and it's a sum of 0:1 or successor :nat. Okay, makes sense. Let's see, maybe you should do plus. So we declare plus to take a natural number and a natural number and give us a natural number, and we define plus equals match x with, if it's 0, and if it's successor of x. Okay, I'm going to shadow this now, just to shock you. Okay. So if it's 0, return y. In the successor case, what do? We do successor of plus of x and y. Okay, so I'm not really shadowing here. Why not? Yes, exactly, because when I pattern match against x, I use the x up, so it's no longer my context. So I can just reuse the variable name even without shadowing, right? Actually, I often do this because there's only so many identifiers I can think of. Okay, so yeah.
Wait, is that still true of the additive approach? Like, what if those variables still
It still works.
technically like linger around?
No, well, yeah, okay. I can make it work, okay. Maybe we don't look under the curtain how it really works, but yeah. So technically, in the type system, it's not a shadowing. In the type checker, it might be shadowing. Yeah. Okay. So then I should be able to compute the number 3, which is a natural number, and we define 3 as plus of successor of 0 and successor of 0. Obviously, this gets tedious very soon, but okay. Okay, it computed 3 as successor of 0. Okay, good. Okay, so let's do some, now we'll tickle the type checker, right? I said if you put 0 here, it should no longer be type correct. Yes? Okay. Oh, I didn't save it. Okay. I was just afraid, you know, I would spend my whole evening debugging, okay? My compiler, thank you. Okay, so let's see what it says. It says that the variable y of mode L stands for linear, by the way, not used in all branches. In the 0 branch, it's not being used, okay? So it's a reasonably informative error message. Should be able to fix that thing in your code. All right, let's see. So technically, it's 10:20, okay? But actually, I started 15 minutes late, okay? Because the department head here extolled the virtues of Boston. So I'm going to just keep going until like Ankush or Marco or Zena yank me off the stage, okay? Okay, so I want to write some slightly more interesting code, like maybe something for lists. Okay, quote nil, 1, quote cons, colon. What did we say? It was not cross list. Yes? Okay, so what's everybody's favorite list function? No, not that one, the other one. Yeah, reverse and append, right? Okay. I think that's all you do with lists, right? Let's do the reverse. How do you program reverse in a functional language? You don't take the first element and you append it at the end, okay? Because that's very slow. So how do you do this? You have an accumulate argument. Everybody familiar with that? If not, you'll see it. And should this function be linear? If I reverse a list, okay, do I use it all up? What about the elements? Do I preserve them? Okay, should be okay, right? I should be able to write this linearly. Now, one of the nice, well, okay, let me stop here. I'll make some remark about this. I think this is technically called, well, let's call it rev. It takes a list of x's and an accumulator, which is a list, and give me back a list. We define reverse of x's and accumulator equals, how do we define this? Match x's with, okay, what's the, it could be nil, and then, or it could be cons of x and more x's. If it's nil, we do what? Return the accumulator. If it's that, then cons of x to the accumulator, right? Do we believe this is the right definition? Okay, well, we can try it. See if it type checks. Nope.
Is nil in the...
Because I didn't fix this function up here. Let's try it again. Actually, somebody had an objection. Did I do it? Okay, I'm willing to, oops, give this a shot. Yes, it type checked, okay. That's usually half the battle. And how do I declare reverse? If I want to just reverse a list. I return a list. Define reverse. How do I define reverse of x's? Ref of x's and what's the initial accumulator? Nil. Okay. And then echo list. Okay, let's say 0, 1, 0, which is a list. Define list 1, 0 equals reverse of, oh boy, cons of quote 0 and cons of quote successor quote 0 and nil. I'm not sure about the parentheses. Okay.
Define intermediate variables.
Yeah, I should define some intermediate variables. Yep. Oh, let's see the error message just for fun. Okay, now that I know it's coming, I feel better about it. Okay, incomplete prefix expression. So a tag is a prefix expression, and it has nothing after it. By the way, I invested way too much time in the type checker. And you'll probably, when you write your own code, you'll say, he didn't invest enough time in the type checker. Okay, so let's see. List 1, 2 is cons of successor of 0 and cons of, yes, it is. Okay, so we can reverse the list. And it's all linear, okay, so this is good. Now, let's do something, we should do something that's not linear. What would be a non-linear function on lists, yeah? Okay. Yeah, then I need, how about if it depends if it's reverse, so I can rev? Okay. Echo dupe, okay, of x's colon list, and gives me a list. Defin dupe of x's equals rev of x's and x's. That should be a horrible type error. Probably the compiler should refuse to talk to me for the rest of the day. Okay. Okay, variable xs of mode L used more than once. Okay. So far, we haven't had any terrible error messages. Okay, so I want this to fail, so I say this must fail. This is the poor man's regression testing. Okay. Now it succeeds. Okay. This actually is significant because a type checker that accepts everything, right? Every correct program that I write will go through, and all the incorrect programs will also go through. And it's very happy, okay? But no, so you do need to check when you write an implementation, the cases that actually are supposed to fail, right? So that's why I introduced that fail keyword, okay? Okay, let's see. Anything else? Yeah?
I just have a question.
Yep.
Like if you want to duplicate a list, we just have to, well, okay, it doesn't work. But in a way, if we pattern match on a unit, we then can create 2 units.
Yeah, yeah.
So I suppose we can do the same for this. We can pattern match on this until the...
Yeah, excellent. That's your homework assignment. Okay, you always have to be careful asking a wrong question, okay? Because I could turn it into your homework assignment. But no, actually, this is a good point. Let's see if it can duplicate a natural number. Why would we do that? Well, there are some functional natural numbers that are not linear. Can you think of an example?
Multiplication.
Exponentiation.
Multiplication.
Multiplication. Okay. Let's do echo mult, which takes x colon nat, y colon nat, and gives me a nat. Defin multiply x, y equals match x with, everybody with me? If it's 0, then what do we return? 0. You should be very scared. Okay, because what happens here? Y is not used, okay? And now we're going to go one step further. If it's successor of x, okay, what do we do? Plus of what? Y and multiply xy, right? We add one copy of y to the result of multiplying the predecessor. Why are we scared now? Because y is used here and it's used here. So not only do we drop y here, ooh, but we also duplicate it here. Oh my God, this function is horrible, okay? So let's see, now the type checker will only give me an error message in the first error that it finds. I don't know which one it is. Okay, variable of mode L used more than once. Okay, so it's the second case that it discovers, not the first one. Okay, but so which functions would we need to know in order to write a linear version that actually does multiplication? So in the first branch, what do we need to do? Yeah?
We can always deep copy or get rid of an integers because it's made of units and part of units combined together.
Yeah. So in the first case, what do we need to do? We need to
Consume.
drop x or something. Match drop x with unit arrow 0. No, not drop x. X is actually gone. Y, right?
Yes.
Okay. And what do we do here? Match. Okay, I shouldn't have called this dupe. Actually, no, let me call it a copy. Copy y with the pair up. I always need a bar, sorry. 1y1, y2, arrow plus y1. Does that make sense? I can do that? Oh, y2, okay. You're better than the compiler, okay? But now, of course, I need to define these functions. So define drop, which takes a natural number and gives me 1. Declare. Define drop of x equals match x with. If it's 0, what do I do? Okay, is that linear? Because I use of x to match against 0, so that's okay. If it's successor of x, then, whoops, I still have x lying around. What do I do?
Drop x.
Drop x. Okay, good. Will this terminate? I think so, right? Because we go to the predecessor. Okay, declare copy x colon nat, return nat cross nat. Define copy of x equals match x with, we're still at, right? If it's 0, we do something. And if it's successor of x, we do something else. What do we do here? 0, 0. And here, match copy x with. It gives me pair x1, x2. And what do we return? Successor x1, successor x2. Look good? Okay. If it doesn't compile, I'll hold you responsible. Okay. Oh, what do we do? Okay. You were responsible. You figure it out. Okay. 55. Yep. Thank you. Wow. Somebody's doing standard ML programming. Okay. Let's try this again. Okay, excellent. So it compiles. Okay. So now this, we might not, oh, they're about to yank me off stage. Okay, but we might not want to actually use this kind of function in practice for multiple reasons. One, unary numbers, you know, they're very, very long, okay? And the second thing is that on every level of recursion, we have to copy y, right? We'd really like the different versions of y to be shared between the two different things. But in a purely linear language, okay, you can't share. So in a purely linear language, you have to copy, right? So the nice thing is you don't have garbage at the end. That's good. But on the other hand, you have to explicitly copy, okay? So there is some trade-off here, like maybe space versus time or something like this. Okay, so homework assignment will be, Chris and I will get together and we'll figure out a couple of programs for you to write. And 1 second. And another assignment, and I'll write it out somewhere, would be to define a family of functions such that it drops for any given type, or it duplicates for any given type. Okay. So if I give you any type A, you should be able to write a function copy sub A and a function drop sub A. Okay. Yeah?
Does the existence of functions like drop and copy kind of subvert the benefit of using programming linearly, or what are the kind of consequences?
Yeah, so the consequence is that if you program linearly like this, okay, then your program is going to be very slow. It's going to use a lot of memory because it doesn't have sharing. So in a later lecture, maybe next one, maybe after, we'll show how to fix that.
Like even suppose your language provided copy
Yeah. Well, it's still the same thing. If it really has to copy things, it's still going to use the space. So what you really want is you want your language to provide sharing. So you don't have to explicitly copy. Okay, so we'll come to that.
Maybe as a follow-up question, can you reiterate the benefits of linear programming?
Okay, so the benefits of linear programming, if you don't have to do this fancy stuff, like a function like reverse up here, okay, is that if your list that you have is linear, it will produce no garbage. So you don't need a garbage collector. But there's another point is, and I will come to this in the last lecture probably, but you can compile this down to C code that all the update, this reversal happens in place actually. So it doesn't actually allocate any new space and deallocate old space. So for example, when you match x's with this cons, that x's will be deallocated and the space where the cons was is free. So when you come to the cons over here, we have to make a new one. You just use the space you just freed. So actually, this function is going to be compiled to be in place. So that's another benefit. You use not only do you not create garbage at the end, but you can also reuse a lot of space as your program runs. Okay. But not all programs are susceptible to this, as we have seen for the times program. So some programs are very naturally linear, and then you have to figure out what to do. Yeah, question back there?
More of a comment.
Yeah.
I would argue that another benefit is sort of if your domain, if you only want to be sure that you actually use a value exactly once, then you get the compiler to help you, right? At which point copy and drop kind of work against that.
Yeah, but then you have to be explicit about it. So in other words, if you expect your program to be linear and doesn't type check because of linearity, then there's probably a bug in your program. So that was the case with the weird plus program that I wrote. It doesn't type check, and it wasn't addition because addition should be linear. If it's not linear, it's probably a bug, right? So you get this benefit of being able to state what you expect the function to behave like, and then the compiler either to verify or deny that. Yeah.
Will this code be made available to us?
Yep. I'll put that in the repo. If you do a git pull, you'll get that code. Whoop. Okay, any last questions? Yeah?
In this language right now, the feature introduced is kind of degenerate because there's no polymorphism.
Mm-hmm.
And so what all the data structures we can construct is essentially structural. They're all built out from the unit type.
Yep. Yeah, so you can write a lot of data structures. You can have trees, things like that. But what you cannot do here is write really higher order functions like map, because we can't pass a function into. So we'll see how to fix that. And it's degenerate in other ways because everything has to be linear. So that's why it's called ADJ0. This is the language level 0. And tomorrow we'll have language level 1. Okay. So we're going to really up the game. Okay. And by the end of the last lecture, we should have the full language. Okay. So we're working our way up because if I try to throw the full language at you, you'll be distracted by all kinds of irrelevant features. Right now, for the current homework assignment, I want you to feel the pain of linear programming, okay? If you don't feel it, okay, there's something wrong, okay? You should think, okay, this is too easy, okay? All right, so I guess I'll see you tomorrow morning or around this afternoon. And remember, there's Chris over there who can answer a question. There's Tesla over there who knows more than I do. Okay. Okay.